Have you ever just stopped and wondered about the stuff that makes up our world? I mean everything, from the copper wire inside your phone charger to the rubber insulating it. It turns out the properties of every single material are all dictated by this incredible story that's happening at a scale you can't even see. It's an atomic story.
So let's kick things off with a super simple question. Why does a metal cable work perfectly for charging your phone, while a rubber band is, well, completely useless for the job? The answer might seem obvious, but the why is fascinating. And yeah, you guessed it, it's hiding deep inside the atom itself.
All right, so let's dive right in. To really get a handle on how materials behave, we've got to meet the three fundamental particles that make up, well, all matter. Okay, so at the very heart of every atom, you've got this dense core called the nucleus. That's where the heavy hitters live, the positively charged protons and the neutral neutrons. But the real action? That's happening on the outside, where these incredibly light, negatively charged electrons are just whizzing around. And trust me, these little electrons, they are the absolute heroes of our story today.
And to give you a sense of just how wild the scale is here, an atom is almost entirely empty space. I mean, get this. If the nucleus were the size of a cricket ball, the atom's outer edge would be a full 5 kilometers away. That's how vast the playground is for our electrons. Just mind-boggling.
You know, our modern picture of the atom didn't just pop into existence overnight. Oh no, it was this fascinating historical puzzle solved piece by piece by a whole series of brilliant minds, each one building on and sometimes correcting the person who came before them.
I like to think of it like a big scientific relay race. Dalton kicks things off, suggesting atoms are just tiny solid balls. He passes the baton to J.J. Thomson, who discovers the electron. Thomson hands it off to Ernest Rutherford, and finally, Niels Bohr grabs it and takes us way closer to the model we actually use today. So Thomson's big idea was what's famously known as the plum pudding model. He imagined the atom as this sort of sphere of positive charge, the pudding, with little negative electrons scattered throughout, like plums. It was a pretty good first guess, but it had some serious problems.
And the biggest problem came to light because of an experiment by Ernest Rutherford. He was firing these tiny, positively charged things called alpha particles at a super thin sheet of gold foil. Now, according to the plum pudding model, they should have all just sailed right through. But some of them didn't. Some of them bounced.
This quote from Rutherford just perfectly captures his complete and utter shock. Can you imagine? He realized that for a particle to bounce back so dramatically, it must have hit something incredibly small, incredibly dense, and positively charged. And in that one moment of surprise, he had discovered the atomic nucleus. So this totally changed the game, leading to the solar system model. You have this tiny, positive nucleus in the center, like the sun, with electrons orbiting it like planets. This totally explained why the atom was mostly empty space and why a few of those particles got deflected. But this new model had its own fatal flaw. See, according to the physics they knew at the time, an orbiting electron should constantly be giving off energy. And if it's losing energy, it should slow down and spiral into the nucleus in, like, a fraction of a second. If that were true, everything around us, you, me, this desk, would instantly collapse. So clearly, something was still missing from the picture.
And that is where Niels Bohr comes in and saves the day. He proposed this radical, game-changing idea. What if electrons can't just be anywhere? What if they can only exist in specific, fixed energy levels or orbits? And he said that as long as they stay in one of those orbits, they don't radiate energy. This solved the collapse problem. It was a huge leap into quantum mechanics, and this exact idea, these fixed energy levels, is the key to unlocking the whole mystery of conductors and insulators.
Okay, so we've got the structure of a single atom down. But how do they all get together and hold hands to form the materials we actually see and touch? Well, it all comes down to the behavior of those all-important outer electrons.
Turns out there are three main ways atoms can bond, and it all just depends on what their outer electrons are up to. In an ionic bond, one atom literally gives an electron to another. In a covalent bond, they share. But for our phone charger question, the one we really care about is the metallic bond, where all the electrons get pooled together. In a metal, the atoms are really generous. They each release their outer electrons into this shared sea that just flows freely among all the positive ions. You can really think of it as a community pool of electrons. And this is exactly what makes metals bendable and, crucially, so good at conducting electricity.
Okay, we've gone inside the atom, We've covered the history, and we've seen how atoms bond. Now it is time for the big payoff. Let's connect all of this back to our phone charger and see exactly what that sea of electrons is really doing.
So, remember Bohr's fixed energy levels in a single atom? Well, when you get billions of atoms together in a solid, those neat little levels sort of broadened out into what we call energy bands. Think of them as energy highways for electrons. The two most important ones are the valence band, that's where electrons normally hang out, and the conduction band, that's the superhighway for moving electrons.
Now in a conductor, like the copper in your cable, here's the magic. The valence band and the conduction band actually overlap. There is no gap at all. This means the electrons in that sea can jump onto the conduction superhighway with almost zero effort. The second you plug in your charger, they form a current instantly.
Okay, so what about the opposite? In an insulator, like the rubber around the cable, there is a huge, forbidden energy gap between the bands. The electrons are essentially trapped in their home, the valence band. It would take a massive jolt of energy for them to make that jump, and that is precisely why rubber doesn't conduct electricity. They're stuck.
And just for a second, let's talk about the fascinating middle ground, semiconductors. Here, the gap is small. It's too big for easy conduction like a metal, but it's small enough that we can give electrons a little push, say with some heat or voltage, to make them jump. This precise control over conductivity is the foundation of every single microchip and transistor in all of modern electronics.
So there we have it. The whole reason you can charge your phone with a metal cable and not a rubber band is all about the electron's freedom. In the metal, electrons are totally free to roam in those overlapping energy bands. In the rubber, they are locked in place by that giant energy gap. It's as simple and as complicated as that.
When you think about it, we went from Dalton's solid sphere to the quantum world of energy bands, and that journey of understanding has completely reshaped our civilization. It really makes you wonder, doesn't it? As we keep probing the secrets of matter, what incredible new materials and technologies will the next big breakthrough unlock?